Hey guys, this is Einar. I hope that you're doing great today, and welcome to this tutorial where we are going to be calculating an hypothesis test for the difference between two sample means using the t-distribution. Now, what do we have here? Well, we have two samples. In this first sample we have the Tango dancers. In the second sample we have the Lindy Hoppers, and then we've asked them, how many friends do you have on Facebook? So this Tango dancers has 76 friends on Facebook, and this Lindy Hopper here has 101 friends on Facebook. So we want to compare this phenomenon. Do Tango dancers have fewer or more friends on Facebook as compared to Lindy Hop dancers? Well, one way of estimating this is calculating the average number of Facebook friends that each group has, and then calculating the difference between these two. And because we haven't asked all the Tango dancers and all the Lindy Hoppers in the world, we're going to have to take uncertainty into account. So the test variable formula that we're going to be using looks like this. And I know it seems huge and it may seem complicated, but don't worry, relax. Its parts are the same as we have been working with so far. On the top here, we have the difference between our two sample means. Now, if our sample means are the same, that would mean that there is no difference in how many Facebook friends Tango dancers and Lindy Hoppers have on Facebook. So this would equal to 0 if they were the same size. We're assuming that they're probably not the same size. That's why we're conducting the hypothesis test. We want to see if there's a difference. In that case, one of these numbers would be larger than the other, and we would get a value here. And the larger the difference is, the larger our t value will become, whether it's positive or negative, in absolute terms, larger. And that would mean that we have a difference. On the bottom part of our formula here, we have our uncertainty. Now, as before, our uncertainty consists of the variation in our samples. Now, how much does it vary? Do some Tango dancers have loads of friends on Facebook and others have fewer? Or do they all tend to have the same number of friends on Facebook? That matters on how sure we can be of our guess. And also, how many people have we asked? So we're going to need the sample sizes. The more people we ask of something, the surer we can be that our average is going to be close to the true value of the number of Facebook friends they have on average in our populations. And that's actually this part of the formula here. This is the true population mean for the population of Tango dancers. So this would be the true mean average number of friends that they have. And this is the same but for the Lindy Hoppers then. So this is the true mean number of Facebook friends that Lindy Hoppers have on Facebook. We don't know these, so we're just going to assume these to be 0 because we're testing a null hypothesis. So don't mind this, read up on it if you're curious, but for now, just ignore it. Focus on the difference between our two sample averages and the uncertainty that we associate with these. So let's start calculating. I'm going to need my sample size of the Tango dancers. That's part of our uncertainty. And I get that we have asked 22 Tango dancers about how many friends they have on Facebook. In the case of Lindy Hoppers, I count that, and I find that we have asked 14 Lindy Hoppers on how many friends they have on Facebook. So these are our sample sizes. They're pretty small. Using the t-distribution makes sense. Okay, so now the exciting part, our estimates. The average number of Facebook friends that a Tango dancers have is 237. So on average, a Tango dancer has 237 friends on Facebook. In the case of Lindy Hoppers, we have 402 friends on Facebook. So that indicates that we actually have a difference here, right? It seems like the Lindy Hoppers are a lot more social on Facebook than the Tango dancers are. They have 402 Facebook friends on average, and the Tango dancers had 237. But, we're not sure about this. We have only asked 14 Lindy Hoppers. So we might have just been unlucky and got a really bad sample with loads of people that just happen, due to randomness, have loads of Facebook friends. And the same thing might be true for the Tango dancers. Maybe we, due to a random problem with randomness, got a sample with Tango dancers that just happen to have very few friends on Facebook. We have to take our uncertainty into account. So I'm going to calculate the variation, or the variance then, in the number of Facebook friends that my Tango dancers have. And I get a number there. And I calculate my variation for the Lindy Hop dancers. And I get another number here. And this is important to mention that this is the one condition that we have to consider when using the t-distribution as a test variable. These have to be of almost equal size. I mean, they're not exactly the same size, but they're pretty close to each other, so that's good enough for us for use. And we also have to assume that these are pretty normally distributed. And the reason for this, in the case of the equal variation problem here, is that we're pooling the variation, we're combining them. So we don't want one sample to have almost no variation and the other to have loads of variation. Then this test wouldn't work. So keep that in mind. But otherwise, it seems like we have all the parts that we need for our formula. We have our estimates, and we're going to calculate the difference between them. We're going to look at the difference between the average number of Facebook friends that our Lindy Hoppers had and our Tango dancers and see if this difference is large. And then we have our uncertainty, so we have variation in our sample sizes. However, because we're using the t-distribution, we have to calculate the degrees of freedom because, as I mentioned in earlier tutorials, the t-distribution changes its appearance depending on what our sample size is. So I'm going to calculate the degrees of freedom. It's going to be the first sample size plus the second sample size minus 1 minus 1. So minus 1 degree of freedom for each sample. That is going to be equal to 34. So we have 34 degrees of freedom. You guys look that up in tables and you'll find that the critical t values are these. Just pause the video and do it and you'll find the same values that I have. But otherwise, I think it's time for us to start calculating our test variable. Okay, I've done a little special thing for this tutorial here where I've written down a little bit about how Excel works with operators. Because this is such a huge formula, it's going to get, we're going to get the wrong values if we don't put our brackets in the right places in our formulas. You see, first Excel calculates whatever is within brackets. So that's great. We could put brackets around stuff that we want Excel to calculate first. Then Excel calculates the exponents, then it divides, and then it multiplies. And this is a problem for us because we have a lot of divisions here that are going to be mixed with multiplications. You see, we want to take this square root and multiply it by that square root before we divide the difference here by that number. So if we don't put brackets around these, Excel is going to divide this difference here by this square root before it multiplies with this square root, and that's not good enough. We can't have that. We need to multiply these before we divide. The same goes for this part here. Because we have addition here and addition and subtraction here, we need to put brackets around these so these numbers are calculated before they are used in division. So just pause the video and consider this and try drawing out the brackets where you would put them, or just look at me now while I calculate this. So I'm going to need a parenthesis, and I'm going to take my first sample mean minus my second sample mean. So I select my first sample mean there, minus my second sample mean right there. Close that bracket. Okay, so we have our first bracket here of the formula. We're taking the difference between these two samples and we're putting it within brackets because there's a minus there, so we need to do this before we do anything with the division here that's below that. I'm going to divide this by, and now I'm going to need another bracket because I want these two square roots that we're going to be calculating to be multiplied by each other before we conduct this division here. So I put my outer bracket here. This is the big circle. That's the bracket I'm working with right now. Then it's time to square root. So I square root, another bracket, and another bracket. Now there are 3 brackets there because the first bracket is because we're doing a square root. You always put what you want to square root within a bracket. The second bracket is for this top part of the formula here that we need it within brackets because we're conducting an addition there that we want to be done before we conduct the division there. So I'm going to need that. So that's the second bracket. And the third bracket is this small bracket here because I want to take n minus 1 before I multiply it by the variation. So I need to conduct the subtraction here before I multiply. And you see, subtraction is way down at the bottom there. So we need to do that first within a bracket before I multiply it there for the correct answer to show up. So I'm ready to do my calculation, which is going to be my first sample size minus 1. Close that bracket, multiplied by the variation in my first sample. So that's this part of the formula here. My first sample size minus 1 multiplied by the variation in my first sample. And I'm going to add, so I'm going to do add another bracket, and then my second sample size minus 1, close that bracket, multiplied by the variation. So I have my second sample size minus 1 multiplied by my second sample variation. And then finally, because we're done with the top part of this formula, I can put another bracket. So I'm going to put another bracket, and we have the top part of this little square root part of our formula here. Now we can divide because we put this within brackets. So I go divide by another bracket, and I'm going to need that bracket because we both have a addition and subtraction here that we want to conduct before we conduct this division. So I'm going to take my first sample size and 1 plus my second sample size there and 2 minus 2. Close that bracket and then close that bracket one more time because this is the number that we want to square root. So I put this within brackets and then I close the square root that we're going to be calculating. Okay, we're going to multiply this by another square root. So I go multiply with square root, another bracket. And in this case, we're not going to need so many brackets because it's going to divide this 1 divided by the first sample size before it adds this to 1 divided by the second sample size. So we don't need brackets around these. We want these divisions to occur before this addition here. So I can take 1 divided by my first sample size plus 1 divided by my second sample size, and then I close that bracket. And then finally I'm going to need a final bracket here because we want to put all of this within a bracket, and I opened it in the beginning and now I need to close it. So we have a large circle closed here. It's going to calculate these square roots, then it's going to conduct the division. So this is actually the formula that we're going to be using. I hit enter and I get a critical value of minus 2.10. This is our test variable. Now, because of our amazing tables that we have over the t-distribution, I don't need to calculate anything for the we're using the t-distribution formula. I can just start comparing this critical value to these values. Now, the question I'm asking myself is our test variable larger than, and I'm talking about in absolute terms, is it larger than our critical values? Well, for a 99% confidence level, right here, we get a critical t-value of 2.72. We ask ourselves, is our test variable larger in absolute terms than this critical value? No, it is not. So I'm going to have to accept the null hypothesis saying that there is no difference. So even though we seem to have a pretty huge difference in the number of Facebook friends that they have, we cannot say that there is a true difference because there's so much uncertainty that we have to take into account. So we're going to need a very, very huge difference indeed for us to be able to say that there actually is a difference in how many friends Tango and Lindy Hoppers have on Facebook. On the other hand, a 99% confidence level is a pretty high confidence level. So we could go down to 95% confidence level and compare our critical values for that instead. And then 2.1, is that larger than 2.03? Yes, it is. So then I can actually refute my null hypothesis at this lower confidence level. Now, if you're curious about confidence levels, I encourage you to check the earlier tutorials. This tutorial is going to be too long if I explain more about this. But I encourage you, though, to try changing these values and see how it affects our critical test variable. For example, I can do one for you now. If I increase the size of the difference between these two, so in fact, Lindy Hoppers have a lot more friends on Facebook than Tango Dancers. Let's say they have, on average, 700 Facebook friends. That will increase our test variable to a very large number. And if this was the case, we could actually refute the null hypothesis because this is a lot larger than 2.72. Well, this is not the case empirically. We just found an average of 402, not 700. So our test variable ends up there. And these are the results that we got based on our empirical sample. Have some fun with this. This is the final video, really. I'm going to do one for one-sided too, but this is the last formula that we are working on in this course. So I congratulate you guys on working your way through these formulas. It has been really fun for me to do. I might make some for one-sided hypothesis testing too, don't worry, but the only difference really is the critical t-values, so I might not, we'll see. I hope you have a really great day. Try experimenting with this, put in different numbers in the samples, and I hope to see you in the next course perhaps, and have a really great day. Bye-bye.